This is one of those questions where you just have to kind of go with your instincts and just follow along and kind of hope that you get a result. Just use all the mathematical operations that you think of and look for kind of a path along the way. So the starting point is that y equals x is an axis of symmetry for this curve. That means it's essentially a line of symmetry. For example, if I had 1 over x, then y equals x would be a line of symmetry. If you tilt your head, you can see their reflections. The right-hand side is a reflection in y equals x of the left-hand side. I mean, I could even rotate it. Why not? I'll do that. So there we go. Okay, well now what that means is if I have a point AB on the curve, then if it's a reflection for y equals x, it switches it around and BA will also be a point on the curve. This red curve is not actually the curve, that's just an example. But we can substitute in now. So it must be that B is equal to PA plus Q over RA plus S. And then similarly, A is going to equal PB plus Q over RB plus S. When I first did this question, I actually found out where they intersected, but that didn't really gild me anything. So it's at that point I thought, okay, it's a reflection. So, you might not think of it straight away, but this is where we have to head in this question. That is like the main property that we have. Because now I've got two equations involving A and B, and I can eliminate one of them. Can't eliminate both of them, can't you know, but we can eliminate one of them. So what I'm going to do is replace all of these A's by this. So therefore B is going to equal P times PB plus Q over RB plus S. And I'm adding Q all over R times PB plus Q over RB plus S plus S. And let's just continue, trying to simplify everything. So I'm now going to multiply through by the denominator, both sides. That'll give me BR times PB plus Q over RB plus S plus BS equal to P times PB plus Q over RB plus S plus Q. I'm going to multiply now through by RB plus S. So then I'll get BR times PB plus Q plus BS times RB plus S equals P times PB plus Q plus Q times RB plus S. Got rid of all the fractions. I mean, it's still looking pretty complicated, but hey, let's multiply out. There's no like obvious other kind of factorization to do at the moment. I mean, there is an RB plus S here and here, and there is a PB plus Q here and here, but that's not surprising because we had that at the top and bottom. So actually, don't go down that path. Let's multiply everything out. So B squared RP plus BRQ plus B squared SR plus BS squared is going to equal BP squared plus PQ plus plus BRQ plus QS. Now, these two cancel. Okay, does that help us? Well, what can we do now? This looks pretty complicated, but the aim now is let's just see if we can factorize it. Factorize as best we can. And I can spot, I mean, I'm not expecting you, but this is going to actually factorize into two brackets. You're not expected to just know that straight away. But again, we're just manipulating and seeing what we can find. And I guess the hint is there in hindsight, the fact that two things are added to give zero, maybe we can factorize something like this out. But for the time being, let's just factorize what we can. I can factorize b squared r from here, b squared r, and I'm left with p plus s. That's those two underlying terms. And then I've got I can factorize a b out, then I would get s squared minus p squared because I've minus bp squared from both sides. And then that is going to equal, I can factorize q out, p plus s. And this is now looking promising actually, because I've got a common factor of p plus s here and p plus s here. And this is actually a difference of two squares. In fact, it's p plus s times s minus p. You might write it as s plus p times s minus p, but I've swapped it around so that now I've got the p plus s here as well. Okay, because now I can just factorize that p plus s out of everything, leaving me b squared r plus b times s minus p plus q. And that, oh no, not plus q, minus q, because I've minused it from both sides, minus q. And that is going to equal 0. Amazing. So either this is 0 or this is 0, but we need it to always be 0. That's the key thing. And r is not equal to 0. So there's no way that this could always equal 0. Like I could pick some values, I could pick maybe s equal to p equal to 1. And then I could set q so that it kind of cancels that bit out, and I'd be left with something that's non-zero here. In fact, I mean, I didn't think of this, but in fact, this, because r is non-zero, this is 0 for at most two values of b, because it's actually a quadratic in b. So this here is not equal to 0 in general. It's the only way it can always equal 0, and to be fair, this is going to be an identity. I didn't use that, but this is true for all values of a and b. I'm not going to write it on every single one, but yeah, always true. So it must be that that is 0. P plus s must equal 0, and therefore p is equal to minus s for us to get the property. But what we're interested in is the answer, which are in the form something plus something is 0, and it's going to be D. Well done.